Every single day, we trust a silent guardian with our most sensitive information. Our passwords, our bank details, our private messages. But this guardian, it isn't a person, and it isn't a company. It's actually a hidden world of mathematics. Today, we're going to pull back the curtain and see how some ancient keys are unlocking our modern secrets.
I mean, really think about it for a second. When you're online shopping and you type in your credit card number, what's actually stopping someone from just plucking it out of the air? We place this incredible amount of faith in the system. So what is that system built on? Well, the answer is both surprisingly simple and honestly pretty amazing.
The whole issue of digital privacy, it feels so modern, right? A problem born from the internet age. So you think the solution would have to be some brand new cutting-edge technology. But what if I told you the key to it all wasn't invented in some lab in Silicon Valley, but was actually discovered in Europe, hundreds of years ago?
This one line just captures the whole crazy idea perfectly. We are using centuries-old mathematics in the most modern applications you can imagine. The security that protects our high-tech lives is literally built on principles that were figured out long, long before computers were even a dream. So let's dig in and see what this math is all about.
Okay, so don't worry, you absolutely do not need to be a math genius for this next part. The core idea is something you learned way back when you were a kid. It's just the math of what's left over.
Remember in elementary school you learned that if you divide 20 by 3, you get 6, with 2 left over? Well, for cryptography, we actually don't care about the answer. That 6 is totally irrelevant. We only care about what's left over, the remainder. So we'd say 20 mod 3 is 2. And that simple little trick, focusing only on the remainder, that is the secret sauce for securing the entire internet. It seems way too simple to be true, but it's the key.
The fancy name for this is modular arithmetic. And the absolute best way to think about it is to just picture a clock. On a 12-hour clock, the numbers don't just keep going up forever, right? They wrap around after they hit 12. So if it's 10 o'clock and you add 4 hours, it's not 14 o'clock, it's 2 o'clock. See? That's modular arithmetic. It's a world of numbers that works in a finite, predictable cycle.
All right, let's run through a couple more of these just to get the feel for it. Look at that first one, 22 mod 6. Okay, so how many times can 6 fit into 22? Well, 3 times, right? That gets you to 18. And what's left over to get to 22? 4. So 22 mod 6 is 4. Perfect. Next one, 43 mod 8. 8 goes into 43 5 times, that's 40, and the remainder is 3. And last one, 55 mod 9. 9 goes into 55 6 times, that's 54, with just 1 left over. See? Simple. Believe it or not, you are doing the core math of cryptography right now.
So who on earth figured all this out? Like I said, it wasn't a bunch of computer scientists in hoodies. They were European mathematicians from the 17th and 18th centuries, and they were just driven by pure, simple curiosity. Now on the screen here, these are our guys. On the left, you've got Pierre de Fermat. He was working back in the 1600s. And on the right, that's Leonhard Euler from the 1700s. These were the pioneers. They weren't trying to invent computers or secure your online shopping. They were just totally fascinated by the weird, hidden patterns they found in numbers. And their discoveries would, centuries later, become the bedrock of our digital security.
What Fermat and Euler did was discover the rules of the game for this clock-like math. Their theorems, they uncovered this hidden, predictable structure inside this world of remainders. And it's that very predictability that engineers, hundreds of years later, would use to build something truly revolutionary. A digital lock that's super easy to close, but nearly impossible for a bad guy to open. Okay, so we have the math, and we have the masterminds. Now, this is the aha moment. How does the simple math of remainders actually protect your private data? It all comes down to creating a special kind of one-way digital door.
Here's the magic trick of modular arithmetic. It creates a mathematical one-way street. It is very, very easy to perform an operation in one direction, but it's incredibly difficult to go backwards and reverse it. The best analogy is mixing paint. It's super simple to mix blue and yellow together to get green, but now try to unmix that green paint back into pure blue and pure yellow. It's basically impossible. That's the exact principle that keeps your data safe.
And this whole one-way street idea leads us to what's called the two-key system. Your computer generates 2 different but mathematically related keys. One is public and one is private. You can give your public key to anyone in the world. Think of it like an open padlock that anyone can snap shut. They use it to lock a message just for you. But here's the kicker. Once it's locked, the only thing that can possibly open it is your secret private key. And the theorems from Fermat and Euler? That is the mathematical guarantee, the lock that ensures no one can ever guess your private key just by looking at your public padlock. That one-way door is locked tight.
So let's zoom out for the final, and I think maybe the most important takeaway from this whole story. It's about why we, as humans, explore ideas that don't seem to have any immediate practical use.
This quote from our source really just says it all. You have to remember, Fermat and Euler were not trying to invent online banking. They weren't trying to secure your text messages. They were just driven by a fundamental curiosity about how numbers work. They were doing basic foundational research for its own sake. Just think about that. Their pure, abstract, useless exploration of number theory had absolutely no practical application in their lifetime, and yet, centuries later, it became the invisible bedrock of our entire digital society. It's just such a powerful reminder that real innovation often comes from the most unexpected places, born from a simple desire to understand the world a little bit better.
And that kind of leaves us with one last big thought. Right now, today, scientists are exploring all kinds of frontiers that might seem abstract or even useless to us. But as this story shows, the line between pure curiosity and world-changing technology is often just a matter of time. The useless knowledge of today might just be the invisible foundation of everything tomorrow. Thanks so much for joining me for this explainer.